Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah.
Hi everyone. It's my pleasure to introduce Stratis, who's a reader at the University of Edinburgh. Some of you might know him because he's had his PhD scholarships with Microsoft, and he's having another one with systems and networking. And yeah, take it away.
Okay. So yeah, thanks for the invitation. It's first time I've been in Microsoft actually. Well, in Cambridge. So so what I'll talk about today is this notion of things that I'm guessing should be near and dear to you all. So this notion of integrating more database-like functionality into programming languages, effectively. So so here's my, I do database systems, by the way. So some of the things that I might say may not be too popular with you. That's okay, that's fine. Just don't throw something at me, right? Or you know, if this is how you do things here, that's fine as well. So I can tell you my view, my own little view of my own little world, right? So the way that I think people build applications, and you can correct me if I'm wrong. So what we usually do is that we have some kind of managed runtime, and it could be C#, .NET, it could be the Java virtual machine, it could be your compiler and your operating system stack, all sorts of things. And you have basically two separate entities into that runtime, which is your application logic, so the kinds of things that you want to do for your in your program, and then you basically manage the volatile memory heap. And what you do then is that you start building your own data structures and your own little, AVL trees or whatever trees you like, or hash tables, or all sorts of nice things. And those data structures basically map well to the kind of processing that you want to do at the application level. And you use your volatile memory to basically store your data structures. What happens is that at some point your data structures become too big to actually fit into your main memory. So then you have to start offloading things to disk. And I'm using SQL and secondary storage. Well, I'm using secondary storage as a general term, but I'm using SQL as a serialization protocol because, hey, I do databases. That's the language that I speak, right? It could be anything else. But the takeaway message is that you need to have some kind of protocol that basically takes your nice in-memory data structures and maps them to something that's block-oriented, disk-oriented, and it needs some kind of translation layer in between to perform the translation, right? So that could be done automatically, and it could be done through some, well, it's usually done automatically through some high-level interface like JDBC if you're using Java, or Link, or some other application, some link provider, so on and so forth. Now, what changes is that the data structures are now, we're now getting enough memory to actually have our data structures completely fit into main memory. So the only reason why we would need this secondary storage representation and SQL or some kind of serialization protocol is so we can target persistence. Okay, so we can make sure that our data structures now can survive a system crash or can survive our system being shut down and rebooted, so on and so forth. But what changes now is that our memory heaps are becoming persistent because we have non-volatile memories, we have persistent memories, we have all sorts of technologies that have historically been 5 years down the road. We haven't seen them yet, but in 5 years we'll get them. That's perpetually true. So what is really interesting is that if you have enough memory to fit your data structures, and if you can ensure that your memory, your byte-addressable memory, is also persistent, non-volatile, then chances are you don't need the right-hand side part of the picture. So what I'll be talking about basically in this talk is some of the things that we've been doing over the past, I would say, 5 or 6 years at Edinburgh with my group in terms of exposing quite a bit of that functionality at the application level. So the first thing that I'll talk about is this this work that we did on code generation for just-in-time query compilation, and that's actually partially funded by Microsoft. So we started by compiling SQL down to C, and then using that representation to run and evaluate queries. But once we figured out that this is not really where the interesting bits were, we started moving towards language-integrated querying, and I'll spend quite a bit of time actually discussing what sort of things, what sort of changes you need to effect to the link runtime so you can get these code generation effects and fast query performance. And the second part that I'll talk about is how we deal with persistence in the context of that sort of architecture. So I'll introduce this notion of rate-limited algorithms for persistent memory. Effectively, I'll only be talking about two algorithms that most database researchers have been beating to death over the past few years, hashing and sorting. And we'll see how we can implement those algorithms in the context of non-volatile memory, but byte-addressable non-volatile memory, using some code generation as a way by which we can better optimize the structure or the performance. Absolutely.
So if you were going to assume byte-addressable persistent memory, well, then you kind of have like a cycle-by-cycle snapshot of everything that's happening. So why is there any research to do? Switch a machine off, switch it on again, and there it is in the state you left it in. There must be something else you're not telling us.
So one of the things that might go wrong, and I won't be talking about this, is that if the reason why your machine died or was switched off is because you had a problem,
like corrupt memory.
like something like that, okay, then you're basically inheriting it, right? So the minute that you turn it back on again, you still have corrupt memory. So just as I was telling Alexander before we moved here, your data is still lost, but persistently lost. Okay?
So you're asking us our base assumption for this talk should be, you've got this byte-addressable persistent memory, you just use it for everything. And you've got to worry about hardware errors in it.
That would be a correct assumption, but I'm not going to be talking about recovery too much in this talk. There's a certain, a separate part of our work that has to do with recovery.
What's left to do? That's what I'm after.
Well, so most of the algorithms that we've been dealing with in terms of databases have been optimized for disk I/O. Try to run a block-level algorithm over byte-addressable persistent memory, you'll end up missing something like 90% of your performance right there. So there are quite a few changes that you need to effect in that respect.
Oh, I see. So there's nothing to do with persistence, actually. You're just saying database algorithms, when you're running them in memory, need thinking about it in a different way. Mm-hmm. Fine. Okay.
So, and by the way, if you have any questions, just shoot, right? So we'll talk about these algorithms for joint processing effectively over persistent memory, and I'll spend quite well, not so much time dealing with some of our ongoing work on extending this work in terms of unmanaged collections, in managed runtimes, and workload-driven data placement. So, so this is, databases 101 for those of you who are not familiar with database systems. So basically, in my mind, again, database systems basically have four standard building blocks: the query engine, the transaction manager, the storage manager, and the recovery manager. And you can think of those four basic building blocks as sort of orthogonal. That means that if, as a database researcher, I choose to work on the query engine, then any performance improvements that I manage to get over the query engine have little effect on other parts of the system. So the added bonus is basically incremental. And it should be the case that if I decide to change the transaction manager, I shouldn't really have to change the other parts of the system that come along with it. Of course, this is sort of an idealized, sorry.
Just to go back to Simon's question, is the assumption that you still want to go through a database even when there's persistent memory?
Right. This is just an introduction for what databases do, so we'll be taking some of those building blocks away as we go along. Right? So this is how databases work. This is, as I said, my own view of the world, coming from a database perspective. What I'll be arguing is that you actually need to throw some of those techniques out just because you're dealing with something that you are not optimized to deal with. Okay? But yeah, great observations so far. So, as I said, these are relatively orthogonal aspects. If you change something on one part, one block of the system, you don't necessarily have to change everything. This is a bit of an ideal situation. It turns out that, if you're implementing your own query engine, part of the parameters that you get for running your queries is a transaction context, and you need to update that transaction context as you go along. For every type of access that you perform over some primary data structure in the database system, you need to have some kind of lock, so that affects the recovery algorithms, so on and so forth. But for all practical purposes, we can assume that they are relatively independent parts of the stack. Now, when it comes to query processing, what happens is that we have this pipeline of transformations that take place whenever you send an SQL query to a system. So the SQL query is first parsed, you have an abstract syntax tree, you rewrite it, you come up with a logical plan, the optimizer takes over, it produces a physical plan, and then that physical plan is interpreted by the query engine to get the results. Now, the first time that I showed this picture to some of my colleagues who were doing compilers, their job basically dropped, because they were always under the impression that SQL is not interpreted. It's actually compiled. But it is interpreted. The reason why it's interpreted was that back in the first days of relational systems, they did try native compilation of SQL. It was just too slow, so they gave up on it. And nobody actually revisited for quite a long time. But so, as we said, so the query is going to be fed through this pipeline. At some point, the physical plan is going to be constructed, which is a plan of operators, so something like a sort merge join or hash join, or some kind of access method that scans a B+ tree, something along those lines. Yes, sorry.
Isn't there a difference with compilers that the optimizer actually takes into account the data that you're...
Yeah. So you can still take into account the data if you're running the compiler, right? But the thing is that a relational query engine needs to have quite a bit, or has at its disposal quite a few more pieces of information when it comes to access patterns, when it comes to staging computation. So even though it started, even though compilation was rejected as an idea at the beginning because it was too slow, the complexity of database systems grew. So that meant that you had all this baggage to drag with you, so you couldn't really afford to revisit everything, right?
What's the real difference between the rewriter and the optimizer? And both of them take a query and produce a better query. Mm-hmm. Is the only difference that the optimizer can use physical information somehow about, I don't know, what about layout?
Statistics, value distributions, memory allocation, so how much memory you have available.
To the rewriter.
Yeah. So the rewriter, so you can think of the rewriter basically addressing the fact that most programmers write bad code. Right? So the rewriter will just take your SQL query and convert it into something that makes a lot more sense, and then the optimizer will optimize that representation. So
after the optimizer's done its stuff, might there be some more rewritings available?
Absolutely.
So actually it's a sort of...
So it's not a loop. So you don't optimize the query multiple times through the actual optimizer. You just, well, the optimizer emits a physical plan, and that physical plan is just trusted. That is going to be the best one, or it's going to give the performance that you need. What really happens in query optimization is that, and that has to do with the shape of query plans, effectively. You have a large collection of query plans that have really bad performance, and you have a small collection of plans, of execution plans, that have decent and comparable performance. So what the query optimizer does is that it tries to steer you away from all the bad choices. Because if you manage to get to one of the really good plans, then any potentially better plan would probably give you something like a 1% performance improvement, which is something that you can avoid. You don't really need that. Okay, so even though you can continuously optimize the query, you choose not to. Because you're really talking about large differences in performance after optimization. So what we did was basically introduce this notion of what we call the holistic technique. So the assumption there would be to have a more template-inspired approach when it comes to query processing. So in the same way that some language like C++ gets a template for a data structure and then instantiates that template based on the data types and on the type of processing that it's performing, we said that what if we have a similar approach to query processing? and have templates for algorithms in the same way that we always have templates for algorithms. But instead of just having a whole bunch of virtual function pointers that allow us to map the query to various different data types, actually have some way of instantiating the template at a per type level. And in doing that, we might as well start collapsing various operators in the query plan so that you can make a whole bunch of nested calls and eliminate function calls that way. So a typical example of why you need, or why we think that you need techniques like that, is the level of data exchange when it comes to tuples records being exchanged between two operators in a query plan. So effectively what happens is that for the operators of a query engine to be composable, you need to have all operators conform to the same interface. So that's what we call an iterator interface, a standard iterator interface, right? But what happens then is that for each record that needs to be exchanged between two operators, you need to make a function call. Okay, so a function call actually hurts performance. But if you know that you are always going to be making the same function call between two operators, you might as well collapse both operators into a single code construct, and you can do that because you're going to be generating the code. Okay? Sure. So you can have.
It's sort of written one.
No. I have an example in a couple of slides of automatically generated code.
But I'll wait for the example.
Sure. Okay. So basically what we're doing is that we're treating SQL as a managed runtime, and we're doing just-in-time code generation for that managed runtime. So the overarching, the new architecture, let's say, of our system now is that, again, you have the parser that takes an SQL query, feeds it to the optimizer comes up with a plan, but now once you have that plan, you take it and you generate code for that. You feed it to a compiler, and then you apply all the compiler level optimizations that you couldn't apply to begin with, or you hadn't applied to begin with. You get a new binary, link it, dynamically load it, run it, give it to the evaluator, and the evaluator just goes to disk, gets the data, and returns the result. And just to give an example of generated code, this is automatically generated code by our system. So we've figured out that there's a single template that you can use to...
So this is the output. What was the input?
So the input, okay. So a typical example would be something like a selection. So a selection is basically...
For this one?
For this one?
Yeah.
So for this
Show
one...
me the output of some algorithm. I'm interested in what the input is so I can see.
So, right, so the name of the algorithm is sort merge join. So I don't know if that helps at all. But the input is two sorted lists that you merge them, and for every pair of matching records, you evaluate a join predicate, some equality predicate. So something like, give me all records in table 1 and table 2 for which the value of attribute 1 in table 1 is equal to the value of attribute 2 in table 2. So that's a join algorithm. So what you do is that you have sorted both tables, table 1 and table 2, on the join attributes, A1 and A2. And what you do is that you make a synchronized scan over the two records, over the two tables, and evaluating the join whenever you have a match between the two. Okay? Another example, or the simpler example, would be something like a selection. So that's a filtering operation, right? So scan that table and only propagate to the output the records for which some predicate is true. Now imagine that you have two selections, one after the other. Okay, so you have a selection on attribute 1 and another selection on attribute 2. What a typical query optimizer would do, or a typical query engine would do, would be to have two selection operators, one after the other. And for every record that would satisfy the first predicates, there would need to be an iterator call, or sorry, for every, the top level operator would make an iterator call to the second operator for every records that would satisfy the selection predicates. So that's a function call. Then you would evaluate the second selection predicate, and then you would propagate the tuple. What we're saying is that if you're doing code generation, you might as well look at that, see that you have one filter feed into a second filter, and collapse those two into a single construct. So these are examples of the optimizations that we perform. Okay? Any more questions on? Sure.
You said that the lists are sorted, the two tables are sorted, right? So is that one of these dynamic properties that you'd be taking advantage of?
Yeah. Because we can generate the code for sorting as well. Or any query engine would actually have some operator that would sort the inputs before it would feed it into a merge join.
of it being a function call, I mean, is it because it's an indirect virtual call that makes it difficult, or would it, if it was a known call, then generate code that, you know, the compiler can inline it if it so chooses?
It must be a virtual function call because you don't know the types when you're programming the operators, when you're developing the operators.
But if you generated code that, say, did the specialization based on type, but still left it as a function call and let the C compiler inline if it wants to? I mean,
But you would still need to be through the C compiler, right?
Yeah, but then you I mean, so you're doing two things. One, you're going and figuring out what type it should be, and the other is you're sort of manually inlining it. And I'm just wondering, is that second step something that you really have to do, or that the C compilers aren't doing it well enough?
Right. So it's something that the compiler can do itself, absolutely, but it cannot do it when you're compiling the server, because it doesn't know what sort of queries you're going to be feeding to it.
No, you need to invoke the query at query processing time. You need to invoke the compiler at query, and you're not willing to do that for some reason.
They're not willing to do that, so we're doing that for them.
So you're going to build a compiler of your own to avoid having to invoke somebody else's.
Absolutely.
Okay, but you could invoke somebody else's. That would be fine too.
That would be fine
slower.
as well. But that would be fine as well. Yeah. It's just that we're choosing to basically collapse as much information as we can into a single code construct.
But by choosing to implement your own compiler, you're losing out on all the 20 man years or 200 man years of effort. Or
right. So maybe I said something that is not true. Right. So we are using a compiler. We are generating this code, this C code, and then we're feeding that code to a compiler.
Oh, you are? Okay.
Right? It's just that we are trying to inline as much code as possible so the compiler doesn't have to reverse engineer all this information.
Yeah. So my experience from this, to add something, is that it's a bit unpredictable when the compiler is going to do inlining for you. And the more contiguous code you expose to him, the more its relocation is going to do. And so
that was our experience as well, but it was our experience with GCC, right? So I don't know what other compilers might be doing. Yeah. So it seems to me that you can feed all those hints, or you can try to make the compiler's life, or you can ask the compiler to do all sorts of compiler optimizations for you. But unless you lay out the code in some way that it can easily figure out that these optimizations are applicable, it's not going to do them, because it tries to avoid basically mistakes. Potential mistakes. So just things to note here is that the fact that we have nested loops all over the place, and nested loops are good as far as the compiler goes. So again, large blocks of code that the compiler can optimize in one go. Fixed strides, so we don't really, if we have information about our records, instead of making function calls to extract attributes from records, we can just directly point to the correct location on a record, dereference it, and always have fixed strides when we're accessing the various attributes, so on and so forth. And type-specific computation, if we know that they're integers, why make a function call to compare integers? We might as well use integer comparison. So these are all things that we can afford to do just because we're doing things at the run, just because we're generating code for the actual query. So that was work that we did for SQL, and a few years ago, we started porting this idea to Link, effectively. So
all this would work for the classic setup with the thing on disk, right? So this looks attractive. Is everybody doing it now? Or are they still interpreting?
You guys are doing it. Microsoft is doing it.
Well, we are. So that's cool. Right.
Yeah.
So now we don't interpret the stuff at the end.
Well, okay. So you do interpret for dynamic queries, but you're using code generation for stored procedures. Hackathon uses stored code generation. I know that SAP uses it for all queries. There are some research prototypes that actually do it for all sorts of queries, all sorts of dynamic queries, but yeah. Sorry.
For the first stage, are you still using a traditional query planner?
Yeah, absolutely.
So it's cardinality based?
It's a cardinality based code model, yes.
So does that lead to complications? Because it might be making decisions based on intermediate cardinalities which just go away, right?
Absolutely, yeah, it does.
Okay.
It does. But we haven't, so if you pick your workload well enough, you don't run into these problems. So if you're using something like TPCH, which is completely predictable, then yeah, you don't really have these problems. But if you have a completely dynamic workload where your value distributions frequently change, then yeah, you might run into problems. So the thing that we're doing just now is that, or we've been doing for the past few years, is that we've been porting this idea to LINQ, right? So I don't have to tell you how a LINQ works, but just as an illustration, you again have the application, you have the query engine and the data store that exchange information in terms of enumerable collections. And what you do is that you have providers that basically take some LINQ representation and they map it to the representation that the data store uses. And one of the standard providers for LINQ is LINQ to objects. And the idea there is that you have in-memory collections, standard lists or something along those lines, and you perform queries using LINQ as the description language as the query language over those collections. So you're not really relying on a relational engine or anything of the sort. You're taking your in-memory collections and querying them on the fly. So what a LINQ to objects code looks like is a little bit like this. So this is a typical example from a schema that resembles TPCH actually. So what you do is that you have a list of orders, you populate it in some way, and then you express some query statement over that list of orders where you iterate over it and you only filter out certain data for which the order date is greater than the 1st of January 1999. And for that, you assign some kind of discount. Okay? So what you would do then is that this is just the specification of the query, so then you need to consume the result of that query through some iteration. So you're saying for each variable in the query statement, so for every binding for that iterator variable, consume the query result. So, so this is, as I said, this is just the declaration of the statement, and just because you have the declaration doesn't mean that you're going to execute it. It just means that you have a representation for it. So only when you start iterating over the result do you start executing that query. So what happens now is that you have a situation similar to the one that I was describing by gestures a few minutes ago. So the idea now is that you still have your orders storage layer, let's say, and then you need to have multiple iterators basically iterate over that storage layer to consume the result, applying some kind of minimal computation at each step. Okay, so first you apply the where operator, and you just consume your input, filter it, and only retrieve the records of that input that have an order date greater than some thresholds, and then for those you apply some second level computation. And that's how things go, right? So this is the equivalent code on the top left corner. So for each record in some source, if the predicate is true, yield that result. Okay? So, so what we do then is that we're saying, if we know that this is what the query is going to be doing, we might as well generate a different kind of code for that. Not necessarily C code, but just C# code to begin with. So we can start collapsing these computations into a single block construct. So instead of having two operations, we might as well generate a single block of code that performs both computations on the fly. Surprisingly enough, this is not something that LINQ to objects did. Okay, so they were actually going through all the motions of running multiple operators at a time. So the architecture, again, is similar to what we had before. So you still have a query tree, you have a code tree, so some representation of the enumerables and operators over the in-memory collections. And then you can generate either C# code or C code. We'll see that, well, once you can generate C# code, going to C code is not as straightforward as you would expect, but it's possible, as we will see. Once you have a C# code or C code representation of the same query, you can convert it into a DLL, dynamically linked library, load it dynamically, run it, and get the results. What we also have is a query cache. So the first time that we see a query, we cache it. If we see it again, we don't have to go through this song and dance of optimizing it and regenerating code for it. And so this seems to be working, just for standard conversion of LINQ queries to C# code. Yeah.
So are you actually generating C# source code?
Yeah. Yeah. And we're invoking the compiler, the C# compiler from the runtime.
Okay. I think there's probably a much more direct route you could use.
It's just that at some point you need to look at the C source code, C# source code to figure out that what you're doing is correct, right? So that's the only reason why we're doing that. So the bad news is that if we have this kind of representation, then we're sort of limited by the performance of C#. That doesn't mean that C# is a bad language. It just means that it's not optimized for database query processing. So a typical example, again, would be something like a collection or a collection of records, whereas if you expect those records to be laid out one after the other in a main memory database system, this is not the case now. So you have these references that potentially point all over the place, and that means that any notion of locality can be sort of kissed away at that point. So what we want to do is have something that resembles the database memory layout, which is something that we can do things, which is something that we can process in a much better way. So what we would like to do is effectively use a value type representation of our records. Now, if our records are structures, that's fine, because that's exactly what C# does. So if we have value type representation, that means that these records are actually stored as a contiguous memory, main memory region. So then, if we generate C codes that actually iterates over that region, that's it. We can...
If they're structures, go back a slide.
Sure.
If they're structures, I think you're saying that
If
each
they are
individual
structures,
record will be contiguous, but the bit on the right, all the records of this relation are also contiguous. And I know
absolutely.
That's a separate matter, right?
That's a separate,
So you're only talking about the little horizontal red guys. You want those to be contiguous.
So you want the horizontal guys to be contiguous in main memory. Yeah.
Okay. But
One
the
record.
vertical, we haven't got to it all yet. In which the successive records
are
still contiguously. That would be true of a database, but not of C# or...
Right, so attributes and records need to be contiguous in main memory. So if you're talking about a structure, right, then the attributes of that, the fields of that structure will be contiguous in main memory, right? And if you've allocated a large number of those structures, then all of those records, all of those instances of those structures will be contiguous in main memory as well.
That wouldn't happen in C# even if you had structures. You'd have to sort of allocate them in some kind of array, wouldn't you?
Yeah. So if the in-memory collection is an array of structures, right, and you've already allocated it, then that makes sense, right?
It's a little hard when you don't know the size of the array.
True, but you can be dynamic in that. If you're willing to pay some extra penalty of having a dynamic array, you can get away with it, right? So if it is indeed the case that we have structures and an array of structures and we've already allocated all those structures, then we can effectively reuse our technique for converting SQL to C, modulo link, to perform, to do things in the same way at the end of the day. Now, the problem is if you actually have an array list or some collection of objects, that's really what makes things complicated. So what we do in those, so this is the notion of saying that you can have some kind of C# level code generation, and then for the heavy lifting of the query, you can, so for instance, things like join processing or aggregation, you can use C-level code generation, combine the two into a single construct, and somehow manage to get the best of both worlds in terms of performance. The reason why you would need to have both C# and C even in that case is that for certain types of processing, something like a filtering operation, it's a bit too much trouble to actually generate C code for that. You're going to be spending most of your time generating the C code as opposed to evaluating the query. So you want to stage your computation in that way. So what if the input is now not structures or arrays of structures, but you actually have collections of objects? So, so the difference there is that you need to have some way of converting those, if you want to use C code to evaluate the query, you want to have some way of converting your in-memory collections to arrays of structures. And what we did was build some substrate that would allow us to exchange information between a C runtime and a C# runtime using fixed buffers that actually take care of the translation between C# types and C structures. And then we can apply again our techniques for code generation over C constructs to evaluate the queries. So what staging looks like is the fact that you first need to know what data is relevant and what records are relevant and what attributes of those records are relevant. So if you have that information, then you can sort of copy all the records, all the information that you need from your in-memory collection onto a C-like array of structures. And once you have that, you can again apply your code generation or our code generation techniques. And if you do that, this is one of the only slides of results that I'm going to show you. So these are TPCH queries. And what we have is the normalized execution of this mixed runtime in comparison to the standard link to objects runtime. So link to objects is the blue line, compile C# is the red line. So just by compiling our queries down to C#, we get something like, well, in the best case, a 70% improvement. On average, we get about 40% performance improvement. So that these are queries 2 and 3. If we have anticipated the fact that we'll be performing query processing over some collection of structures, and we have laid out our data structures that way, then we move on to the green line, to the green bar. So for that, we have really dramatic performance improvements. So we can get up to 90% performance improvement on all those 3 queries if we manage to have laid out our objects or our data in some way that is conducive to processing with C. But if we're not that lucky, we actually have some technique that allows us to copy data from the C# runtime to a C-like representation and then apply code generation using this mixed mode query processing. And in the best case, again, have a 90% performance improvement, but on the average, and Q2 is a typical performance improvement over all the queries that we've tested, gets up to something like 60 to 70% performance improvement. Yeah.
These are for sort of full scans, right?
Full scans and aggregations, and some joint processes as well.
Okay, but if you're doing an index lookup, do you do that in the C# world or the C world?
No. So we assume that we don't have any indexes. So these are all standard scans, right? So of course, if you have something like an index and you perform a single lookup, then no runtime is actually going to save you, right? So it's not as if doing a lookup in C is going to be that much more effective than doing a lookup in C#. So the assumption here, and the majority of TPCH queries are scanning queries. So they assume that you're doing analytics as opposed to point lookups or something along those lines.
Could you compare this to systems like Steno or the link optimizer from Nessos?
So we have, right, so Steno is one of the things that we tried to compare it with. Surprisingly enough, we didn't have the implementation of that. But they're doing things that are fairly close to what we're doing, but they're not really targeting query performance. They're mostly dealing with representing things at the C# level in a better way. And I could be completely wrong on this one, but our impression was that the going all the way down to C, just because you wanted to get as much performance as you could out of the system, is not something that was one of their primary goals. But I could be completely wrong on this one, and we didn't have access to the implementation.
Okay, the second one I mentioned was a system called Link Optimizer by a consultancy called Nessos. You should take a look at that.
We should, yeah. Another approach would be something like Ferry, but again, they're targeting different parts of the query pipeline.
There's a system called Closure Reducers as well.
I am aware of those, but we haven't made a comparison. Yeah.
I was going to ask you to compare with Dryad Link, because obviously it was in the mode. It was thinking about the MapReduce style world, but obviously it was thinking about efficient and very large data.
Absolutely.
And running queries over that, right? And it did a lot of transformations and emitting C code and C# code and recompiling those and loading the DLLs and distributing them to different machines and so on. So it seems like a more obvious starting point than linked to objects.
Absolutely. So one of the things that we're looking at just now is basically using more expressive workflow languages as opposed to SQL, and then we will be comparing to dry link because we're going to be mapping quite a bit of our processing to MapReduce workflows, and this is the obvious choice. So over here, we're just saying, in the worst, well, in the typical case, you have a developer who has their own data structures, and they're going to be using link to objects to begin with. So how can we improve that? Okay, but you're absolutely right that Dryad's link is another comparison that we need to make.
Another question about your staged computation. So in your staged computation, you're taking essentially a manage object, and you're extracting the fields that are interesting from it and representing those in unmanaged structure to make it efficient. Have you considered just simply doing the opposite? Keep all the data unmanaged and use the .NET property style APIs to make fake objects in the rare cases where it doesn't matter and you're going to inefficiently access the object from the C# world.
So we haven't thought of it. It definitely is something that we're looking into just now. So one of the things that we're doing just now is taking this approach all the way to one extreme and saying that everything is just unmanaged memory as far as we're concerned, and we have our own implementation of collections that allows us to perform these computations as quickly as possible. Yes?
So the data that you actually copy across and stage, when you actually execute the query, do you iterate over that data many times or something? Because it seems just intuitively, once you go to the effort of copying, then all the non-locality, you've paid all that price. Like all those cast mishes, you have to pay those just to do the copy.
Yeah, but you can mask some of those differences, right? So what we do is that we don't copy it in one go, and we have multiple threads, some kind of producer-consumer analogy. So we generate chunks of data so that our C runtime can process those chunks, while at the same time we're copying other data. And if this is a long-running computation, then in the end we'll end up winning.
So the code that the C compiler produces is just that much better, even if you already have to go and run all over memory.
Yes.
All right. Okay.
And but by the way, this is not just for C#, right? So Java sucks even more. So, but you probably know that already. So I don't think I have too much time actually to go through the second part. Oh, sorry, there's a question.
So what's the cost of compilation in this?
So which part? The link part or SQL to C?
SQL, both. I don't know, compared to the runtime of the query, to the evaluation time.
Right. So if you give me a slow enough compiler, I'll give you more data. Right. So then I'll win again. But that's a great observation. It's in some cases, if you're talking about some query that only runs, in a few milliseconds, and you have all the compiler optimizations turned on, you might actually lose. So you might be spending most of your time just compiling the query. But the counter argument to that is this is a one-off cost. So you only have to pay it the first time that you see the query. If you have recurring queries, that's why we have this query cache. You can just invoke the execution. Yeah.
Have you looked at all just using one-time generation of managed code?
Sorry, come again?
Have you looked at all, instead of going all the way to C, just using JIT compiled code?
So we yes and no. The reason why we couldn't do that is we don't have access to .NET. Right, so we...
What do you mean you don't have access to .NET?
Well, we can't generate .NET level code, CLR, right? Externally, completely externally. Or at least when we started this job, this work, we couldn't.
But now you can.
Now we can, but this is from 2 years ago, really.
Okay.
Right, so this is work that started 2 years ago, and at that point, yeah.
You do it differently now.
No, hang on. No, there's always been libraries for compiling code on the fly in .NET. Either using reflection or
right,
generate
okay.
You can generate bytecode as you're going along.
Bytecode as you, well, that's pretty much what we're doing, right?
No, because you're
we're invoking about, well, okay, so we are invoking the, both the C# compiler that generates bytecode, right, and the C compiler, if we have to.
Right, I'm just saying you shouldn't need to do either of those. You can just generate bytecode in memory and compile that.
Right, so we haven't done that. We haven't looked at that. Yeah. So more questions? So should I wrap things up? Because, yeah. Okay? So I can give you basically, so if there's a single thing to take away from the second part of the talk, is that I'm not going to be talking about, is this notion of what we call a write-limited algorithm. So, so imagine that you have, non-volatile memory, and the key premise is that updating takes longer than reading. So writing is more expensive than reading. And let's assume that you can sort of quantify that ratio. So let's say that writing is 10 times, for instance, more expensive than reading. What that means is that in the same amount of time that I need to generate an intermediate result, which is something that we frequently do in database systems, I can reread the input that many times. So if the write-to-read ratio is equal to 10, that means that in the same time that I need to generate some partition or sort my input, I can read it 10 more times. Okay? So the assumption, based on that assumption, we have a whole family of algorithms that allow us to trade reads for writes dynamically. And what we do is that through, so I'll skip the algorithms, through some runtime, through some well-defined API, it turns out that you can express all database query processing algorithms using that API. And it all comes down to 5 calls, basically: partitioning, merging, splitting an input, filtering an input, so on and so forth. But what you do is that in typical code generation fashion is that once you have expressed your code using that API, you don't actually compile it. You just record the workflow of that code, and whenever you need to access one of those collections that you generate on the fly, you can make a decision whether you want to materialize it. So let's take something like T0 over here. We know that in order to materialize T0, we need to scan T and partition it using some hash function. That's what the workflow, the control flow graph basically gives us. Right? So now I have an option. I can either materialize it, or I can choose to rescan T, a much larger input, and apply the computation to reconstruct it. So what the runtime does is that it dynamically keeps track of the reads and writes over each collection, and it decides whether it needs to materialize it or not. So yeah, we track the accumulated number of cache line reads and writes, and decides based on the operation whether we need to materialize, whether it is of more benefit to actually materialize that collection, or we can afford to reconstruct it from its input. And we can do that at all levels of a query plan, effectively. So for instance, if you want to generate the final plan, you can replay the entire trace of computation starting from the principal tables in order to compute that. So we've also tested quite a few implementation alternatives in terms of exporting NVM, exposing NVM to the system. So the first would be something like a RAM disk, a persistent memory file system by Intel, having our own, having a standard dynamic array representation where you assume that you're using a standard memory allocator, and then you're accessing, or you're just using non-volatile memory as standard DRAM, or you can have an optimized memory allocator, which is the last representation over there. That is a memory allocator aware of the fact that it's allocating data over non-volatile memory, so it generates chunks of, it returns chunks of memory that are a lot better laid out for the various types of algorithm. So the goal of this work was not so much to show that you can have the best algorithms you can think of, or the most high-performing algorithms the highest-performing algorithms you can think of when you're operating over persistent memory. It was to show that you can choose the right intensity of the algorithms without compromising performance. So what this complicated graph basically gives you, and you have your buffer memory size on the x-axis and performance basically on the y-axis, is the fact that you can have, you can take your standard, really optimized external sorting algorithm if you're sorting data, and you can get the same performance at 20% of the write cost of that algorithm. because you now have a runtime that allows you to dynamically keep track of your reads and writes. So you can choose when you want to trade some writes for extra reads, or if you're not really interested in, leveling out the wear of your device so you can afford to perform extra writes, you can then get some more performance that way. And the fact is that regardless of what sort of write intensity the developer or the programmer wants to have, you can still get decent performance. You can still get as good performance as you would have gotten if you were only optimizing for I/O. Yeah.
So does this rely on the fact that the pipelines, processing pipelines, are relatively shallow?
Yeah.
Because you don't have to memorize too much?
No, not too much, no. So it's a combination of memorization, basically, and dynamic cost-benefit analysis. And the fact that, your workflows are not going to be, are not going to be spanning a few, megabytes of memory or gigabytes of memory to traverse them, that helps as well. So, so ongoing work, so this is something that I alluded to at the beginning. So what we're doing just now is that we're saying that if you really want to do things correctly, then you should have a chunk of unmanaged memory managed as a database system, really. And you need to have your own memory collections exposed to the developer, and then all those nice properties that you rely on to get the performance that you want in code generation for Link are actually taken care of from the beginning. Other things that we've been toying around with is, things like instead of having an array of structures, having a structure of arrays, so vertical partitioning effectively. So we can do all sorts of things on the fly if we are allocating memory ourselves. And finally, data placement for non-volatile memory. The notion now is that you have some kind of hybrid system where you have, your DRAM and your persistent memory, your non-volatile part. You're still managing collections, and what you need to decide is what to place where. So you can have some intermediate result that is only going to be accessed one time. So something like a partition or some intermediate run when you're doing external sorting. So even though you're accessing it as a file, you might choose to put it in DRAM just because you're only going to be accessing it once and throwing it away afterwards. So just to summarize, the entire notion is that large memories mean that processing is now going to be becoming even more memory bound. The fact that we have non-volatile memory coming into the picture, and unfortunately this is not something that I talked about too much, means that we need to set up our data structures in some way that guarantee persistence and need to be accessed in a non-volatile way. And we also need to change our algorithms so that they make as much use of the characteristics of non-volatile memory as possible. So what we're proposing is a management approach at all levels. So having decisions being taken at memory allocation time about how to lay things out, and during runtime, having decisions in terms of what to place where and what sort of code you need to run in order to evaluate queries, in our case, as efficiently as possible. And so acknowledgements, the students did all the work, I'm just doing the talking. And collaborators, Gavin Biren, who used to be here, Marcelo Sintra, Alexander from now on, and Vijay back at Edinburgh. And this is the shameless plug. So if you know of any good PhD students who are interested in doing a PhD either in data science or parallelism, please ask them to send me an email. And I'll just leave the summary here, and thank you.
So we have a few more minutes for a question.
I have a comment. It's nice to think of all these little SQL queries being generated by a JavaScript program and then going through your analysis to undo all the bad work that they've done beforehand.
That's so another. That's a very good observation. It doesn't necessarily need to be, JavaScript. It could be any your favorite or least favorite scripting language. But the observation for this work was that we looked at the use cases of database systems, and in the vast majority of cases, you have some poor guy typing in information in a form. right? And then that gets translated into an SQL query. So in the vast majority of cases, your SQL is really fixed. So that's why code generation actually starts making a lot more sense. And of course, you can undo all the bad effects of bad programmers, but still.
Let's thank speakers. Let's thank the speaker once again.
Thank you.